start, sir?
Okay.
I'm just
Yeah.
going
And
to
then,
give a brief. I'm just going to give a brief introduction of yours
okay. Perfect.
so that our audience knows, and it is also being recorded to be uploaded on YouTube, on our
Okay.
university's YouTube channel, so that later
Okay.
on, if somebody has not joined us right now, they can access the videos later. I
Okay.
don't want
Perfect.
anyone to miss this information. It is going to be such an informative information, I'm sure, for everyone. So that's
Thank
right.
you.
Yes. So good morning, everyone, one and all present here. On behalf of Galgotia's University, I, Dr. Vandana Sharma, welcome each and every one of you, and especially Professor Ferrari for joining us and giving us his precious time from his busy schedule. Professor Ferrari is an associate professor of telecommunications at the University of Parma, Italy, where he coordinates the Internet of Things lab in the Department of Engineering and Architecture. Currently, Sir is member of Scientific Council of Inside Industry Association, member of the Board of Scientific Council of National Inter-University Consortium on Telecommunication. Also, Vice Director of the Interdepartmental Center Future Technology Lab of the University of Parma, President of the Bachelor's Degree course in Computer Engineering, Electronics and Communication of University of Parma. Professor Ferrari research interest revolves around three main areas, which he has published extensively in and receiving few awards and relevant research fundings: signal processing and data analysis, advanced communication and networking, IoT and smart systems. He is an IEEE senior member. Since 2016, he is co-founder and president of Things to I Limited, a spin-off company of the University of Parma dedicated to IoT and smart systems. Today, Sir is going to talk about and is going to present the main research activities which are being carried out at the IoT lab in the context of body sensor networking, from the applications of monitoring of motor impairing pathological disease like Parkinson's and stroke. He will also show few results on gait analysis and current ongoing applications related to indoor localization and vehicle driver monitoring. Thank you so much, sir, once again for accepting our invitation. We are very much overwhelmed and we are sincerely looking forward to collaborate with you in future. Over to you, sir. You can please start with your session.
Okay. First of all, let me thank you, Professor Sharma, for this invitation, which is a pleasure. Been a bit late in setting the date, but you have been very patient. So, okay. So
Thank you.
today
Thank
I'm
you so
going to.
much for joining us.
Okay. So today I'm going to give an overview of the main activities in our lab in terms of body sensor networking. So basically, this is the outline of my presentation. First, I will give a brief introduction on our research group. Then I will discuss like past, present, and future activities. And finally, I will conclude the presentation. Now, the introduction. Let me first give a quick introduction regarding Parma, our city, the University of Parma, and then our research group. Now, the city of Parma is placed in northern Italy. As you can see, like it's between Milan and Bologna. It's right in the middle. And Parma is typically very famous for food. In fact, like it's very famous for Parmesan ham, which you can see here, and Parmesan cheese, which you can see here. Besides food, it's a medium city, very pleasant, and it has one of the most beautiful Romanic squares in Italy. Now, the University of Parma is also one of the oldest universities in the world. It's one of the oldest in Italy, and it was founded formally in the 12th century, so approximately 1,000 years ago. Right now, the university is organized in 9 departments, and there are a number of students, which is around like 30,000, like plus minus a few thousands per year. And it's a research also oriented universities because there are several PhD programs. Every department has typically more than one PhD program. Now, the distribution of the university in the city is the following. In the center of the city, there are mostly the, let's say, humanities department. So there is economics, law, there is also the university hospital, literature, psychology. And you can see here, this is the headquarters of the university, like where the rector of the university sits. Instead, at the south city edge, there is a university campus where there are all the technical universities, all the technical, departments. So there is engineering, math, physics, chemistry, pharmacy, and so on. Now, if you Google Parma, you see that there is a sort of like beltway around the city. So the city is inside this like beltway, and in the center of the city, there are the humanities, let's say. Then at the south edge, just right outside beltway, there is the university campus. And if we zoom at the university campus, there is a lot of green. It's a very nice campus. And there is also like a soccer field, a tennis fields, a golf court. And this is the Department of Engineering and Architecture. And our research group is inside one of these buildings. Now, our research group, the Internet of Things Lab, I'm coordinating it. And right now we have one young faculty member, Professor Davoli, and also one senior researcher, Dr. Laura Belli. And we have also a few PhD students. Actually, one of them, Sunil, is Indian right now. And we have also other collaborations with other faculty members and other research groups. Along the years, we had the opportunity to collaborate with several companies and partners, let's say. So with academic partners, institutional entities, and also industrial companies. And right now, these are the ongoing projects that our research group is carrying out. Now, I'm not going to give details on all of them. I'm just highlighting here two of them. One is Next Perception, and another one is CPSAC. Now, Next Perception, these two projects, I will go back later on when I talk about present activities, because several of the activities on body sensor networking are associated with these two projects. Then this is the list of completed projects. And again, here I'm highlighting two projects because these are the projects, especially this one on body sensor networking and machine learning. I will describe them as past activities. They are the most relevant activities in terms of body sensor networking. Then we had other projects. Along the years, over the last, I would say 10 years, on all the activities, most of the activities became more and more applied, let's say. So basically, almost all projects that we have right now aim at developing at least one prototype. And based on the basis of these activities, we were able to basically assemble a very interesting testbed, IoT testbed, as we have more than 150 IoT nodes with very heterogeneous connectivities. So we have cellular connectivity, Wi-Fi, 802.15.4, sub-gigahertz, ultra-wideband, BLE, NFC. And besides this applied research aspect, of course, we have also tried along the years to push the theoretical scientific aspects of all the activities. So we try to, of course, we aim at scientific excellence, as I think it's normal for every academic research group. In terms of research activities, our research group, basically the activities revolve around three main areas. One is signal processing. The second one is advanced networking and communication, and finally IoT and smart systems. And the arrows that you see in this figure are related to sort of the, let's say, historical evolution of our activities, in the sense that I have a background in telecommunications, so I did my PhD working on signal processing for communication aspects. Then I had the opportunity to move towards networking and wireless ad hoc networks. And then with a European project at the beginning of the 2010s, so about like 10 years ago, we had the opportunity to start working like seriously on IoT. And from that point on, we also worked on smart systems as like we denote by smart system prototypes, which combine sensing, communication, processing all together. And we went back to signal processing here, but not in terms of signal processing for communications, but more sensor signal processing. And in fact, body sensor networking will really be significantly about like these two aspects. So in body sensor networking, communication and networking is not really relevant per se, at least in the activities that we carried out. What becomes more interesting is sensor signal processing, and we will see that like the type of sensors that we are using, and IoT and smart systems. Now, why is IoT so interesting? This is a slide which I use like in several talks because I find it very interesting. Now, to give you an idea, there are like 3 lines in this talk. One is this orange line, then there is a blue line and a green line. Now, the orange line is associated with physical connectivity. So basically, it represents like the progress that the humanity did in connecting one physical place to another physical place. And you can see that like it took approximately 150 years to be able to go from one place of the earth to any other place of the earth. Then the second line, the blue line, is associated with the internet. I mean, internet was born at the end of the 70s, and you can see that like thanks to the development of the internet and also thanks to the social networks which were created, basically people were able to be connected worldwide in much less time. You can see that like it took about like 30 years for every person in the world to be connected virtually with any other person in the world. And around the 2000s, maybe 2010s, that's when like people really started talking about IoT. And you can see that the connectivity curve of IoT is much steeper. So it is projected that in about like 20 years, there will be tens of billions of things which will be connected to the internet and which will generate automatically information and which will also communicate with each other automatically. So it's a very interesting time because we are in the middle of this explosion. Actually, we are looking towards apparently the end, but maybe there will be new developments. Now, when you think about IoT and body sensor networking, as you will see in the presentation, we have been working significantly on inertial signal processing. So basically, when you use inertial measurement units and IMUs, and then you basically analyze the behavior of those signals. This is an example. This is a picture which I took in 2015 at Expo 2015 in Milan, Italy. And there was the UK pavilion, which was all like it revolved completely around bees. And this figure here shows like an accelerometer. And as you can see, it's a very tiny device, let's say. And the idea of this accelerometer here was of measuring the vibrations of the beehive. So if the beehive was working, if the bees were fine, the beehive was vibrating with a given like pattern. And if something went wrong with the bees, then like the change of pattern of accelerations would like notify that something was changing. So it was an interesting application. And as you will see, several of the activities on body sensor networking revolve around the same idea. You measure, you observe the pattern of movement, and if there is a variation, then you try to understand why there is this variation and what could be the motivations. So this is related, really, first, this inertial signal processing is related to like the past, let's say the activities that we carried out in the past, and we are starting again but with another perspective, as we will see later. So in the past, we worked significantly on two aspects: motion analysis and inertial navigation. And I will start by describing quickly some of the activities that we carried out in the context of motion analysis. Now, our dawn, let's say, in this context, was really the idea of doing a hybrid radio inertial processing. So as you can see here, we had the opportunity to have a donation by Sun Microsystems, and they gave us a gift these devices here, which were called Sun Spot, small programmable object technology. And for the first time in these devices, there were accelerometers. So we started playing with them, and basically we put two target nodes that you can see over the front arm and over the upper arm. And then on the body, we put two anchor nodes. So the idea, actually, there were around several anchor nodes. You can see the figure in the middle. There were two target nodes, and there were 7 anchors. Now, the idea was that basically through fingerprinting techniques, radio fingerprinting, with machine learning, in particular the KNN algorithm, we were basically training the system to recognize where target 1 and target 2 were in the space. And then with the accelerometer, we were working out pitch estimation. So we were trying to understand where the arm was and what was the orientation of the two parts of the arm, and we were combining them. And it was an interesting, it was the first time for us that when we approached really the accelerometer sensor processing. Now, we also realized that fingerprinting, radio fingerprinting, was not really very robust, because you have to be in a very stable wireless environment, and then things do not have to change. Otherwise, you run the risk of let's say getting wrong results, because the fingerprints have changed. Now, in terms of performance results here, we eventually verified our system, the performance of our system in terms of precision as a function of accuracy. And the accuracy is basically defined as the distance between the estimated position and the true target position. And the precision is basically the percentage of successful estimates for a given accuracy. As you can see, we get to a precision over 90% with an accuracy of 20 centimeters. So the system was not working really well, in the sense that the accuracy was not very high. But in order to check what was the performance of our system, we compared it with that of a Microsoft Kinect, because at that point it was sort of the state of the art to recognize the movement of the arm in front of the Kinect. So it was a video-based technology compared to a hybrid radio inertial technology that we developed. And as you can see, the performance is comparable. So there is not there is actually some improvement for small accuracy, but then at the end, when you want to get to a precision over 90%, the performance becomes more or less the same. So this was really for us the beginning, and it was around 2015. Now, our real boost, let's say, came when, after playing with the Sunspot, the devices that I mentioned before, we had the opportunity to get new devices. These were shimmer nodes. So the shimmer were one of the first class of nodes which had an embedded inertial measurement unit, and they were able to transmit the data. And as you can see here, we started working on sensor signal processing, inertial sensor signal processing, with algorithms which have just appeared in the literature. And these algorithms allowed to evaluate basically the orientation, the 3-dimensional orientation in the space of each one of these devices. So if you had 3 devices, you could basically reconstruct in real time the orientation of the body. So the first one here on the chest would allow to reconstruct like the orientation of the chest. The one on the upper arm would allow to reconstruct the orientation of the upper arm, and the one on the lower arm would allow to reconstruct the orientation in the lower arm. And here you can see a video. Matteo was the PhD student working at that time on these devices. So there are 3 of them, and you have to look at the computer, and you see that like the system in real time was reconstructing the orientation of the body. So you see that when he was raising the arm, like, okay, let me see here. There was a problem in the video. Okay, now there should be the video. Probably like Matteo was moving around. And you can see that like basically there is a reconstruction in real time of the movement. Now, based on this, we started like working on body sensor network based activity classification. Actually, the first approach, like, I mean, what you have seen before is a bit more advanced in the sense that we came to that reconstruction in 2015. But before reconstructing in 3D, another line of activity was related to BSN-based activity classification. Now, there was in 2011 what was called the Body Sensor Network Contest. It was like a contest which opened at the conference BSN 2011. And the idea was that like basically they were giving data collected by 4 IMUs placed as indicated here. So one on the wrist, one on the chest, one on the upper leg, and one on around like in the bottom leg, part of the leg. And you didn't know anything about like what was happening, but your goal was to reconstruct the behavior of the person. And there were several activities which were possible. For example, it could open a drawer, it could lay down, it could get up. And your idea was, I give you this data and you have to tell me what the person did around the day. So basically we won this competition. That was like a lot of merit goes to Matteo, like the PhD student that like you saw in the previous figure, in the previous slide. And the idea of our algorithm was very simple. Basically, we devised an algorithm working in 3 phases. The first phase was that dedicated to collecting the data, cleaning the data in the sense that like sometimes the sensors were providing spurious data or spiky data. So the first phase was really to clean the sensor data. The second phase, which was the most critical, was that of segmenting this data. So basically, we wanted to sort of creating windows which would classify where there was an activity. And the third phase was, given that we have segmented the data, then we want to classify each segment with an activity. And this is a graphic representation of what happened. So for example, this was the first signal. It was an acceleration, for example, the X acceleration from a sensor. And you can see that there are a lot of spurious like spikes. And then there is a significant acceleration here. So in the first phase, the idea was we take the original data and we clean them. We make this data like more readable. Then in the second phase, as you can see, we sort of window them. So we identify the periods where there are activities. And then the third phase, which is not shown here, is for each of this window, we decide what was happening. And that was based on a machine learning algorithm, actually a KNN algorithm. Now, once we started playing with this sensor signal, our boost, let's say, in our activity came when we had the opportunity to collaborate with the Istituto Auxologico Italiano. That's a medical research center. It's actually very research oriented, and they were working on pathologies with motion-related symptoms. In particular, there were 2 like pathologies which were interesting, which were of interest. One was Parkinson's disease, and the other one was stroke. This was a very intense collaboration and very interesting for us because we were really able to start working on inertial signal processing significantly. And here you can see some of the publications that we managed to get together with this research group. Now, what was the problem? Well, I mean, the problem was related to the fact that mobility has a significant impact in quality of life, of course. And the motor performance evaluation is fundamental, for example, to when there are pathologies and you need to provide therapies based on the quality of movement. So before we started collaborated, the clinicians were relying on qualitative analysis. So basically a doctor was looking at a patient, and on the basis of the experience of the doctor, he or she would prescribe the patient a specific dose of medicine. Now, at some point, the doctors, these doctors were neurologists. They started asking themselves, but is there a way to have an objective view of the pathology, in the sense that if the pathology has a given degree is at some degree, then the movement should be quantitatively representative of this degree of the pathology. And then we started working in this direction. Now, before we started collaborating with them, they were already using some of these approaches, but they were using at that point optoelectronic devices. So you cover a body with reflective markers, and then there are cameras around the body, and the cameras basically reconstruct the trajectories of these markers. But as you can see, it's a very invasive system because you have to cover the body with markers, and it's very expensive. Then there were other systems, for example, ground reaction forces, foot switches that you see here. But all these systems were kind of complicated and in some cases very expensive. Then at some point, the inertial measurement units, as we have seen before, started performing extremely well. And thanks to macro electromechanical system, MEMS, they became extremely small. So they became extremely interesting for this type of applications because they were cost effective, easy to use, small sized, and flexible. So the proposed approach in this project was the following. We wanted to design a smarter assessment tool. Basically, we wanted to be able to see or to detect automatically what was the gravity of the disease. And of course, it had to be low cost and low complexity. It had to be accurate, smart in the sense that we basically used machine learning to provide an automatic motor impairments level assessment. And it was also telehealth ready, because a system like this can be used, for example, for measurements at home. Now, in terms of motor evaluation, the Parkinson's disease is a neurodegenerative pathology, and the characteristic symptoms are tremors. At some point, there is rigidity, bradykinesia, so movement becomes slower. And in order to classify the gravity of the disease, there is the Unified Parkinson's Disease Rating Scale, UPDRS. And the UPDRS basically is a discrete scale which goes from 0 to 4 with integer values. So it's very simple. There are 5 values, 0, 1, 2, 3, 4. And the goal of the neurologist is to classify the gravity of the disease. And depending on the gravity of the disease, the medicine had to be basically decided. Our focus on the automatic evaluation of the Parkinson's disease gravity was based on the lower limbs. So we had leg agility, and we were considering 3 specific tasks. One was leg agility, one was sit to stand, and another one was gait. Now, in order to do that, eventually, we realized we implemented a 3-node body sensor network, and we were using 3 shimmer nodes, like 1 on the chest and 2 on the thighs, on the legs, sorry. And this shimmer node has a 3-degree accelerometer and 3-degree gyroscope and 3-degree magnetometer. So it was 9 degrees of freedom system. And based on the algorithms that we had developed before, we were able to basically estimate in real time the orientation of each one of these devices. Now, in order to have a fair comparison, we also validated our system with the state-of-the-art optoelectronic system by basically adding these reflective markers on the body to see how our system was performing with respect to state-of-the-art systems. The data set that we were able to work was the following. We had 34 Parkinson's disease patients over 47 trials. And the patients were in very different conditions, in the sense that they were in on-off state, which depends on the levodopa on a medicine that they take. And we had the evaluation of the same patient by 3 expert neurologists. And as you can see on the right here, basically the idea was to have the 3 neurologists to score the patients. And then there was this UPDRS mean, which was our automatic system. You can see visually that our system is very similar to the behavior of a neurologist. Now, I'm gonna give you the details only on some of these tasks because we don't have enough time. For example, the leg agility task. The leg agility, the patient has to sit and then it has to raise 1 leg at a time. And what you see here, it's the signal, which is the angle of the orientation of the leg. So when you're seated, it's 0. When you raise your leg, when you pull up your knee, the angle increases because it's your leg bends like this. Then you reach a maximum value and then you go back to normal. So what we did, we looked at this signal and we extracted the very reasonable features. And these are the features of these signals. For example, we had the angular amplitude in degrees, the angular speed of execution, the speed at which you reach the maximum and you go back, the pause of execution between 2 consecutive leg raising, the regularity of execution, the repetition frequency, the time inclination spectrum power, because we moved, for example, once we have the signals, we can transform them in the frequency domain, and then we can analyze them from a frequency point of view. And then we had the tie angular velocity spectrum power. So for each one of these features, what we did, we sort of analyzed how the features were representative of the UPDRS scale. Now, what you see in this radar diagram here, it's for each feature, for example, consider gamma mean. Gamma mean was the angular speed of execution. You see the behavior in sort of normalized in a scale between 0 and 1 as a function of the gravity. So for UPDRS 0, gamma mean is 1, maximum angular speed of movement. For UPDRS 0.5, it becomes this. For UPDRS 1, it becomes this, 1.5, 2, 2.5, 3, 3.5. So it means that, for example, omega mean, omega and submean is very representative of the UPDRS because it changes as a function of the UPDRS. You see, for example, that P submean is less representative because the values are very close to each other. Now, in order to quantify these observations, we simply consider the correlation with the UPDRS. And as you can see, omega submean has a very high correlation, high in terms of absolute value. It's negative, but it's okay because it's very high. So it means that among all these features, omega submean is the feature which is the most representative for the analysis of the Parkinson's disease. This is another task, the sit to stand. So basically the patient was sitting on a chair and it has to stand up by without using the arms. So it had to put the arms over a chest and then try to bend over and get up. And again, here, what we did was we looked at the signal. This is the orientation of the chest. And we simply considered intuitive features. We made the same analysis. These are the features that we consider. For example, the total duration, the forward bending duration, the backward bending duration, the forward-backward duration difference. So very intuitive features. We made the same analysis that we did before, and we basically identified the feature T sub B in this case, the backward bending duration, which is most representative for the UPDRS. Finally, the third task was gait, which was the most complicated one. So the patient had to walk 10 meters ahead, then turn on itself or herself and come back 10 meters. And basically from the signals from the sensors placed all over the body, because for the gait we used all three of them. For the leg agility only these two, and for the sit to stand only this one. But for the gait, every sensor that we have. We basically worked on gait, and the idea was that first you have to segment the gait in the sense that you have to understand when there was a step, and then you have to evaluate several, in this case, features related to step. For example, there is the mean gait cycle time, the mean stance time, where you are basically you are making a single step, the mean double support time, the limb time, the stride length, step velocity, cadence, step regularity, symmetry, tire range of rotation, total spectrum power. Now, the gait is very complicated in general, and you can describe the gait with several features. So again, we made the same analysis that we did before for the gait, and it turned out that, for example, in this case, the stride length is the most representative feature for Parkinson. So that was very interesting again. Now, at that point, what we did, this, for example, is a combination of three of these features. Instead of looking just at one, we consider stride length, right thigh rotation, because you see that it's very high as well. And then we add step velocity or power. We use this one. Now, the idea in general is that if you have more features, then you can sort of identify a trajectory in the space of features of the disease. So you see that you start here with 0 as UPDRS, and then the evolution of the disease brings you towards this point here. It's very intuitive, because as the disease progresses, the stride length reduces because you make shorter steps. The rotation reduces because you move slower, and the power of your step also reduces because you slow down in some sense. Now, in order to generalize this approach, we used another technique. We used principal component analysis, because once you realize that you have a lot of features, you don't necessarily need to consider the explainable features that we consider. But you can take all your features, you can train an algorithm, and the algorithm, on the basis of principal component analysis, can extract three components which are very representative. Now, these components, once you apply PCA, no longer have any intuitive explanation or are explainable. But you don't care, because at that point, your algorithm is doing the best it can, in an automatic way. Now, once we've done that, basically, we were able to sort of define the features select the best classification algorithm, and then train this algorithm. And we basically trained the algorithms on the basis of the information provided to us by the neurologists. So we were looking at one patient, we were collecting the data, and a neurologist was telling us, okay, this patient here has a UPDRS equal to 2.5. So we were training our algorithm saying that like those features correspond to 2.5. Then for another patient, there were other features like movement features, and another neurologist was telling us that it had like 3, and then we were training the algorithm with 3. At some point, once you train this machine learning algorithm sufficiently, then you can test it on new patients. And so basically, we were like, at that point, we had a sort of virtual neurologist, in the sense that once you train the algorithm, then you can apply the algorithm to a new patient, and your algorithm can predict a given error, or a given, UPDRS. So one question of the neurologist was, okay, if I use your automatic system, what is the error with respect to a neurologist? Now, in this figure here, the top figure here, this is the CDF, the cumulative distribution function of the error between our system and a neurologist. And you can see that like basically it reaches 1, actually it's over 90% for an error like equal to 1. It means that with probability at least 90%, the error of our system with respect to a neurologist is at most 1. Now, we didn't know exactly if that was good or that was bad. So what we did, like we asked like 2 different neurologists to provide the same, like to sort of classify the gravity of the disease for the same patient. And it turned out that the CDF of the 2 neurologists is on the figure at the bottom. And you can see that it's very similar. So if you take 2 different neurologists, it's very likely that their judgment will be different of at least like 1 in at least 90% of the cases. So basically, it means that our automatic system is behaving as a virtual neurologist. Now, another interesting, like once we had the opportunity to work on the 3 tasks, there was also a question by the neurologist, which was related to what is the inter-task correlation? I mean, is it meaningful to look at the 3 tasks that we mentioned before, the reg agility, the sit to stand, and the gait? And it turns out, and we try to evaluate the correlation between the different tasks. It turns out that the tasks are not like very correlated. I mean, they are moderately correlated, which is very good because it means that every task is providing like further information on the gravity of the disease. Now, based on this idea, what we did, we also introduced like a sort of a total UPDRS. So basically, instead of looking just at one task, we look at all the tasks that we have, and we combine the values of the 3 tasks. And as you can see, this total UPDRS, of course, it can be much higher than 4 because it's the sum of 3 quantities. In this case, you see 4 quantities because we distinguished between right leg agility and left leg agility. But again, this idea, I mean, this approach gives you an intuitive idea that if you combine different tasks, you can get an aggregate like behavior, which is very representative, from low gravity to high gravity of the disease. Okay, so once we, I mean, while we were working on Parkinson's disease, we had the opportunity also to like consider the, to work on another disease, I mean, neurological disease like stroke. Now, why for Parkinson's disease, motion analysis is very important to basically provide the right medicine. For stroke, motor evaluation is very important in terms of rehabilitation. So after a stroke, like rehabilitation is crucial immediate rehabilitation is crucial to allow the system to recover your body. And the idea was to use IMU-based gait analysis, so the gait that we already investigated in Parkinson's disease, to evaluate how the patient was progressing in his or her recovery. Now, the fact is that stroke typically has provides like a sort of an hemiparetic gait, in the sense that typically stroke affects one part of the body. And it means that after a stroke, typically gait becomes asymmetric and irregular. So it's very difficult to analyze the gait of a post-stroke patient because it's asymmetric. So what we did, we first started considering a very extensive body sensor network. You see that here we have 6 shimmer devices, and this was a very rich analysis, in the sense that we were able to basically derive all the gait parameters, the joint angles between different parts, for example, of the legs. But the problem with this approach is that it was very uncomfortable and time consuming. So after discussing with the doctors, we basically realized that the most efficient approach was to use one sensor node. And eventually, the best position was to put it here on the back, around the 3rd vertebra. Now, this is very quick installation because they just need to use a belt. It was low cost and it was very realistic for real life monitoring. It's a system which could be used all the time to monitor the behavior of the person. Now, we were able to validate again this system with an optoelectronic system, and the results were very good in terms of reliability. So our system was very reliable. In this case, the data set was more limited than the one that we had for Parkinson's disease. We had only 5 post-stroke patients, and we had 3 healthy controls, so persons not affected. Now, for stroke, the gait temporal parameters that we investigated, eventually, I'm not going into the details, but we moved to the frequency domain. So we were considering basically, we were collecting the acceleration signals and transforming them in the frequency domain. So we're making an FFT, and the frequency domain, a very interesting feature became the power. The power in the telecommunication sense. So you have a signal, you make the FFT, and then you evaluate the power in the frequency domain. And it was very interesting because that gives you an intuitive idea of why for example, you mentioned sometimes that an athlete is very powerful. An athlete, like a runner, is very powerful because if you take his motion signals and you transform them, and then you look at the power of the FFT, the power is very high. So the athlete is very powerful. And we were also basically, another difficulty here was basically to sort of identify which one were the segments to consider to investigate the steps. And we followed here a simple moving average approach on the linear acceleration magnitude signals based on the power, frequency power results. So we were looking at the frequency power results to decide how to segment the gait. And finally, we were refining this by identifying the heel strikes and the toe hops, which are the 2 behavior, let's say, at the beginning and at the end of a step. Now, these were the time parameters, the temporal parameters, to sort of identify when a step was starting and when it was ending. Then there are the gait spatial parameters, because once you do that, then you have to estimate what is the length of a step. And there are 2 algorithms in the literature. There were 2 algorithms. One was the Zijlstra algorithms and the Weinberg algorithms. And as you can see here, these 2 formulas are heuristic formulas. The Zijlstra algorithm is associated with the height of a person, h, and L is the length, the step length. Whereas the Weinberg algorithm basically is associated with the maximum linear acceleration and the minimum linear acceleration. And both of them were like, are heuristic. So our idea was sort of like taking this to, eventually we used the Dijkstra algorithm. I mean, the Dijkstra formula, because it was more reliable, at least in our case. But instead of considering just like one formula for both like steps, left and right, we sort of consider that like for the normal part of the body and for the hemiparetic part of the body. We made a comparison with optoelectronic systems, and you can see that the correlation here was very high, in the sense that like the reference system and our system, like the predictions lay basically on the bisector line. So it means that the correlation is very high. And in fact, the correlation between like our system and like an optoelectronic system was over 0.9 for almost all parameters. So again, it meant that our system was working very well and it was reliable. Now, what we are doing right now, like I'm highlighting this like in red here, because like, as you will see, one of our future activity is really to carry on with this work, but in free living environments. So we give up like an ambulatorial, like sort of like closed environment, and we want to allow a patient to be able to walk freely around. Okay, this was most of the activity for motion analysis. Then once we were working on gait analysis, we basically started thinking about like, well, once we are analyzing the gait, why don't we work on inertial navigation? Inertial navigation is basically like it pertains to recognition of the trajectory. You want to identify the trajectory of a person or of a vehicle in an environment which is GNSS denied. So for example, in an indoor environment. And the main goal is you have to use inertial signals of properly placed IMUs to estimate the traveled path. This is an example of an estimated path, and we'll get back. We will see like a few videos shortly. Now, we have already talked about like the shimmer IMU, which was the main IMU that we used for Parkinson's disease analysis, but we also had the opportunity to work with other IMUs. The X-Sense IMUs, which was the best IMUs that we had, and also this one, which was very interesting, LPMS-V2, because it had a Bluetooth interface. And here there are the features, I mean the characteristics, the technical specs, but I'm not going into the details of this. Now, again, for inertial navigation, we started investigating about the placement of the IMUs. So we put them on the feet, as we did for Parkinson's disease, which was very good for estimating the length of the step. But we also realized that like on the trunk, I mean, having an IMU on the trunk would allow us to estimate very well the heading of the person. So eventually we combined the two, like the information on the heading and the information on the step length, and to derive a sort of like a hybrid inertial navigation system. And here you can see this is a track and field path that we had here at the university campus. And you can see that like when we were using the hybrid system, like this like blue stars, like the path estimated was quite good because we were getting back to the same position with a limited error. And here you have an inside like the paths estimated inside the corridor in our department. This is like our building that we are in. Now, we made several evolutions, for example, considering multiple IMUs per foot. And also what you see here, this is a barometer, and it's a very cheap barometer. And our goal was to estimate like the floor we were in by checking like the variation of atmospheric pressure. Now, what I'm showing here is like we participated in this conference, IPIN 2016, which was in Madrid, I mean, near Madrid. And the idea, there was this competition, like track 2, pedestrian dead reckoning. The idea is that like a person had to give, to follow a path which was given right at the competition. And along the path, there were checkpoints. And in proximity of the checkpoints, each system had to sort of communicate the estimated position. And the best system was the one which was minimizing, let's say, the error with respect to the known checkpoints. Now I'm showing you a video. I'm not sure if you hear also the sound. Can you please let me know if you hear the sound?
No, sir.
No.
Sound is
okay, then
yeah.
No, then I'll talk over it. So here you see basically that that there is like the person is moving, and the trajectory is reconstructed only on the basis of like the one, like multiple like shimmer nodes on the foot. Now here at some point, I'm going forward a little bit. Here there is a staircase, a circular staircase, and then the person goes on the first floor, and then it walks a little bit on the first floor. Then at some point it goes back to the same like staircase, and you see that there is an error here, because like the error basically, as we will see later on, like the inertial measurement systems have a key problem, which is a drift, because the error accumulates. But overall, basically, we were able to reconstruct the entire trajectory with a very limited error. And this was a very long walk. Overall, it was like several hundreds of meters, almost like 1 kilometer indoor. And the error eventually was very limited, because we estimated like to go back to the same position with some precision. And in this case, we did not consider any information on the environment. This is another demo that we did like here at the university campus for a NATO meeting. And here, as you will see, the idea is that I was using a single X-sense IMU on the foot. And we were also using the barometer to estimate basically the pressure variation. And as you can see, automatically through the barometer, we were estimating the floor. The GPS was collected by a smartphone, and as we'll see, the GPS estimates our red dots, and on inside, when we are indoor, like the estimation is completely like wrong. And then when we move outside, then the position estimation becomes much more accurate. Now, as you will see, here we are in the first floor of an indoor building. Then the person is doing like a circle here, and then it will go down here by the stairs. The red dots, you see that they are completely off, because like once you are indoor, like the GPS is not working. So the person makes a circle, and you see that the reconstruction is perfect at this point. And then here there are stairs, and you see that the floor, from floor number 1, when the person goes down the floors, the floor goes to 0. So it reaches like the bottom floor. Then at some point, you see that the red dots are completely off. Then at some point, the person moves outside this building, and as you will see, the red dots starts approaching like the person, because like the GPS becomes like more reliable, and it allows to estimate precisely the position of the person moving. Now, there is this walk outside, and I'm speeding up. Then the person enters again into the system, and then it goes back to where it was before. Now you can see that like overall, this was another very interesting result for us, because we were able to estimate the trajectory by just using a single IMU in a pretty accurate way. Actually, as you can see from here, the ideal would be to sort of combine the two. So once we are in indoor scenarios, you cannot rely on satellites, and then you have to use inertial measurement units. But once you are outdoor, you can rely on satellites. And as we will see, these are some of the current activities that we are doing right now. This is another video, because like once we did that, we were able basically to generalize this approach. So instead of tracking just one node, we were able to track multiple nodes. So there could be multiple persons moving, and each person has one IMU on the foot. Now, at that point, it became interesting. I mean, it's the use of a single IMU on the body is very effective, as we have seen in several scenarios. But it was also very interesting to see how inertial navigation could work by using a smartphone. Now, things here are very challenging because basically you can, I mean, with a smartphone, you are very free to move the smartphone as you want. So if you move the smartphone because you need to talk or you need to look at something and then you turn around, then it's extremely difficult to sort of like estimate how you are moving with a smartphone. Now, we did some analysis, and for example, if you're keeping the smartphone in front of you because you're looking at it, then we devised an effective algorithm to estimate like the step detection and step length once you're moving. But in general, estimating the trajectory through a smartphone is very challenging. It's very challenging. Now, a recent project where we had the opportunity to sort of use like the inertial measurement units, the IMU-based trajectory estimation, was a collaboration with Vodafone, where basically they were interested in using virtual reality systems. So when you put a visor in front of your eyes, you basically get immersed in a virtual reality and you forget about the physical reality. But if you want to do that, and if you want to move inside a real like environment, you need to be able to know where you are in reality while you're moving inside a virtual environment. So we tried to apply our inertial navigation system to sort of understand how we were moving inside an environment. And it was very interesting. Like, again, this is a very challenging scenario because like your estimation needs to be like very precise. So at some point we realized that it was also very difficult to have an IMU on a foot. And then we started using another type of sensors, which are ultrasonic sensors. And that's like the paper that we have here. So basically we sort of like used ultrasonic sensors, which are very interesting sensors, to sort of like estimate the distances from objects. Okay, moving to the present. Right now we are working on two projects which are related to body sensor network. One is hybrid localization, and another one is related to driver status perception. So let's talk about hybrid localization, and I'll show you like two videos to sort of motivate why we are going in this direction. So as we have seen before, if you consider inertial navigation, it works very well, but a key problem with inertial navigation is the fact that there is an error accumulating. Now, in this figure here, you have to think that the person is moving like along like the x-axis on the 0. So it keeps on moving on this axis, on this line. But as you will see, the estimated trajectory like degrades in the sense that there is a drift. Any like inertial based measurement unit at some point keeps on accumulating an error. And as you see, the estimated trajectory over a path of around like 40 meters in each direction degrades. So you are still moving on this line in reality, but your system is estimating that you're moving like down. Now, if instead of using only an inertial measurement unit, you were also able to estimate the distance from a fixed node, an anchor, for example, with radio communication, then as you will see, every time you pass by this anchor, the radio like localization allows you to correct your position. So even if you are like drifting away, when you pass by, you can use like radio localization to sort of correct the estimation. And as you can see, for the same type of walk, you see that like the drift is much more limited. So this result here suggested that instead of just using like simple inertial navigation, you can consider hybrid navigation where you have inertial measurement units and also like radio-based localization. And we had the opportunity to work on this with this approach in like a working safety scenario. So for example, there are systems, there are scenarios where it is very important to know where a worker is to avoid that it goes into dangerous zones. This project is called CPSAC. It's Cyber Physical Security, and it's financed by INAIL, which is National Center for like Worker Safety. We are collaborating with the University of Siena. They are focusing on dangerous substance sensing, and we are focusing on localization. So the idea is that of like devising a system which can allow to estimate the position of a person or a vehicle, both in outdoor scenarios and in indoor scenarios. And so the goal is what I just mentioned. And for outdoor localization, we relied on satellite communications. Actually, we relied on real-time kinematic systems. A real-time kinematic system is a sort of an advanced satellite positioning system where you have basically the worker, and the worker is equipped with the GNSS like transceiver. And then you have a base station, which is like whose position is known extremely accurately in a very accurate way. And the idea is that like the worker receives like its GNSS, I mean, it can estimate its position through its GNSS signal. The base station knows its position perfectly, almost perfectly, and then the base station sends a correction to the worker so that like basically you can improve significantly the position estimate. So if you use a GNSS, a single GNSS system, the position, the location accuracy is around 2-3 meters. But if you use this RTK system, then the localization accuracy becomes like a few centimeters. Of course, you pay in terms of infrastructure because you need to have a base station. But for outdoor applications, for outdoor localization, this is the technology that we are using in this project, RTK. Now, for indoor localization, we are using a hybrid system, as we have seen before. So we are using inertial measurement units to estimate sort of the heading of a person, how a person is moving, in which direction. And we are using ultra-wideband signals, radio communications, to sort of like estimate the position. Why is it interesting to combine the two? Because we basically devised an algorithm which allows to estimate the position with at least 2 anchors. If you don't use inertial measurement units, then if you want to make radio localization, then you have to use at least 3 anchors to estimate the position of a target. And the general result is that a hybrid approach typically outperforms an approach which is based on a single technology. Eventually, we came up with we are working on an integrated prototype that you see here. So you can see here a Raspberry Pi, which is acting as a host. And here you have like the U-Blocks system, which is basically the RTK system that we are using for, let's say, for outdoor localization. And then for indoor localization, these are the decawave anchors that we are using to obtain like position estimates. Then the system is connected to a Wi-Fi network. So we are under the assumption that there is Wi-Fi coverage. And basically it transmits the position either estimated with like the GNSS, the RTK system, or with ultra-wideband plus inertial inside the, to the cloud. Now, this is the dashboard that we developed. This is the real environment of the experiment that we did, like the demo that we did in Rome at the research center of INAIL. And this is the base station. This is the antenna of the base station placed on top here, where you see the red like indicator here. And this inside here refers to the structure of the distribution of the anchors in indoor scenarios. So our demo was to walk outside and then inside, and the system is able to switch between outdoor GNSS-based localization and indoor hybrid ultra-wideband inertial. These are the position estimates in indoor, and you can see that it works pretty well in the sense that it estimates like Luca moving inside the corridors. On the outside, as you can see here on the left, Luca was moving, was sort of like going up the stairs, this like metal structure. Now this seems simple, but it was very challenging. It was very challenging because the metal structures here had a strong like impact on radio transmission. So basically we realized that the position of the base station has to be accurately selected in order to have like good performance, a good like position estimate of the worker. Now here I have a video just to give you an idea of like these triangles that you see here are the anchors, the ultra wideband anchors. And as you can see, like Luca is entering from the left and it will go up in the corridor and the position estimates are pretty good. At every instant, we are using only the two nearest anchors so that the system is basically relying on the inertial measurement units to estimate the direction of movement and to two anchors to basically localize like the target. And then it continues, but we go on for simplicity. This is instead like an estimation based on RTK, but in a scenario less challenging than the one that we have seen before. This is in front of our like building. And in this case here, I mean, this is the base station position and the target is the blue one. Now the target is now standing and Laura is the target in this case. And as you can see, Laura is going to start walking. This is the antenna, the GNSS antenna on top of a helmet for security purposes, for safety purposes. And as you can see, at some point, Laura is going to start walking. And you see that the system is estimating her trajectory pretty well. Now, Laura at some point is going to make a turn here. You see that it's walking over this like cement system and it's working pretty well. And then like Laura is going back. So if the base station is well positioned and there are no obstruction, RTK is working very well. Okay, we continue. The second project, the final project that we are working on right now is related to, it's a European project and it's called Next Perception. So the idea of the project is that of like basically implementing new generation smart perception sensors with distributed intelligence. That's one of the keywords. And the idea is that of having proactive behavior and physiological monitoring. So you don't want just to predict what is the current status, but your goal is to predict what the evolution will be. And we are collaborating in this project. We are working on a joint driver and vehicle monitoring system. So our goal here is to perceive the status of the driver and to combine the status of the driver with information coming from the vehicle. And in particular, we want to monitor the stress level of the driver. And we're doing that by measuring like the heart rate beating and by using a thermal camera, which analyzes like how like the face, let's say, of the driver is working. We are also developing here a multi-interface gateway, but that's not relevant for the purpose of body sensor networking. Now, this is the use case that we're working on. In general, it's driver monitoring, and I already mentioned like a little bit what we are doing. So I'm just going to skim through because we are running out of time. Now, basically, the idea is if we collect the data from the person, so we are collecting the heartbeat, the thermal camera images, and we are able to know the status of the vehicle. For example, we are collecting acceleration signals from the vehicle, so we know if the driver is driving smoothly or it's speeding up or it's accelerating. Then can we estimate jointly the status of the vehicle of the driver? Well, to do that, we are using two types in this case of sensors, as I mentioned before. One is an equivital life monitor. And equivital here, basically this is a sensor electronic module which goes inside the sensor belt. And it's positioned here, the sensor electronic module, and it allows to collect several informations like the ECG, the respiratory rate, which is very important, the skin and core temperature. There is an accelerometer, which is not very important because the person is sitting. So what we're really interested here in this data, in this sensor data, are the ECG and the respiratory rate. And this is an example of an interface which was provided by, which is provided with the system. And basically, as you can see, it checks in real time the heartbeat, the respiratory rate, and the skin temperature. So we are basically collecting this information and we are combining it with the other information that I mentioned before. The other type of sensor that we're using is a thermal sensor. And in particular, we are using a FLIR One Pro dongle, which can just be connected to an iPhone or in general a smartphone. And basically the idea is that it allows to sort of like see thermally, like through a thermal sensor, to have an image of what's happening. Like these are the technical specs. Just like I just want to mention that the frame rate is around 8 Hertz, so it takes 8 like frames per second, and you can see that the thermal resolution is pretty high. It can also be used as an RGB camera, so it has like both thermal sensor and RGB sensor. And this is a first video. I mean, I'm showing you like, I lost my cursor, just a second, sorry. Okay, so you can see here, this is Veronica driving, and you can see that like there is a reference on top here, a reference like zone, a reference area, which is at 18 degrees, and then by comparison, actually the FLIR allows you to put like several points, and it allows you to estimate the temperature at different points. Now, changing like while Veronica is driving. Okay, eventually, what we are doing right now, sorry. No, I lost the cursor. Anyway, so one of the efforts right now is on multi-sensor fusion, because we have data from thermal cameras, we are data from wearable devices, the equivalent that we've seen before. We are thinking about including smartwatches. And then we are working on this JDDS, which is a joint driver and vehicle system. And the idea is that like basically this JDDS becomes the core, let's say, sort of like the brain of the system, which allows to estimate what you can see here in this formula, which is the average arousal. It's a formula to estimate how basically the stress level of a person is changing as a function of like all the data which are perceived. We have a few publications on this related to this project as well, there on the bottom. Okay, finally, like the future. Now, based on all the activities that you have seen, at some point we realized that one of the difficult things for us was to use like commercial systems in some sense for as inertial measurement units, because like every system had like some criticalities in the sense of data transfer. So what we are trying to do with like the spin-off that I mentioned, like with the spin-off of our group, we are trying to develop, for example, a node which we call Move2I, which is basically a lightweight, because it's very light, mobile tracking node. It has like a GNSS system inside, so it can locate itself on the outdoor. But the interesting thing is that it has both Wi-Fi and Bluetooth interfaces. So it's relatively easy to collect the data with this device, and we're going to start using this for monitoring Parkinson's disease patients, but on a very, let's say, large like time horizon. So the idea is to leave like one of these devices, to put one of these devices on top of patients, or Parkinson's disease patients, and have him or her walk for, I don't know, like 2 hours, and then collect the data over a long time horizon. which is impossible with the other systems. We are also working at, like Laura and Luca are like developing all the interfaces that you are seeing here. And you can see that like basically there is an app which allows you to see in real time all the data that you are collecting with the system. And you can also geolocalize the system, because like if like it is of interest like to use like the GNSS data. Now the applications, like as I mentioned, the main application is in long-term and non-invasive monitoring of patients, for example, when they are at home or when they walk outside. But we are also using this system to monitor, for example, athletes' training sessions, and we are collaborating in particular with a soccer team near Parma. In general, we think that this like system is very flexible, and it can support a lot of applications, let's say. Now, finally, to conclude, so we have seen in the past like applications like related to motion analysis and inertial navigation, and both like these like approaches, they were looking at telemedicine and also at target tracking and location-based services. Now, in the present, we are working on hybrid localization, in particular safety applications and biophysiological sensing. And the future is sort of like having a platform which we call like move to I, which could allow us to develop new applications and in general like be more flexible in what we do. So finally, like body sensor networks, it's a very interesting topic in the sense that it combines, like from our point of view, body-oriented sensing. It can be both with sensors on the body or with sensors around the body, for example, a thermal camera, and with IoT. And this opens very interesting like research areas. Because for example, you can study trade-offs between like complexity of system and accuracy of estimation. Or you can have cooperative applications, because for example, you can use more sensors to sort of estimate in a more precise way the status of a person, or you can use like different body sensor networks on different persons maybe to develop cooperative applications. So this concludes my presentations. Thank you very much for your attention. And of course, like if you have any question, like I'm happy to discuss.
Thank you so much, Professor. Thank you so much.
Thank you.
You have actually given us so much to process. So many things I cannot just imagine. This was completely out of the box for me, and I'm sure for most of our participants. The ideas that you're working on, they are very novel. And the area in which you're working, it's commendable. Thank you so much for sharing it with us. And
thank you very much.
So I will be taking some questions. If at all participants have some questions, they can post it on the feedback on the chat window. Case. Yep. In the meanwhile, I will have some questions from Vic. Can I ask, sir?
Yeah, sure.
So I'm interested in knowing, sir, are we going to have in near future any like injectable kind of a sensor for humans? Because somewhere we are tracking, we are monitoring, we are very much interested in 24/7 monitoring of human body. So
yeah, I mean, like I had like when I was in a NATO research group, there were like several research groups there, which were working on injectable pills. For example, to measure the body temperature, the inside body temperature, because in some critical applications that was like critical data. So there were these like special forces. They were injecting these small pills, like which were transmitting on the outside the temperature of the inside of the body, because they could not run the risk to have a too high inside temperature. Now, in terms of injectable, like if you mean in the body, I know that there are several applications, for example, for let's say, I mean, there is some new system for dosing the insulin, and I'm sure that there is a lot of there are a lot of activities probably on injectable systems, but like we're not working on that right now.
Okay, I'm sure you will be working on that in near future. Okay, sir. And sir, one more thing I would like to know for our students, BTech students, Bachelor's of Technology students. So,
Yeah.
if they want to work in the body area network domain, then from where shall they start?
Yeah. It depends. Like I mean, we found very interesting. We find very interesting like the activity which is based on inertial measurement units because they are non-invasive.
Mm-hmm.
And right now, I mean, some of the algorithms that we have, which I showed you, for example, the reconstruction in 3D of the body
Yes.
positions, at that point in 2015, they were quite new, let's say. But right now, there are systems which have already embedded like very robust versions of those algorithms. So it's sort of like easy to get one of those systems and just start to play with them. So you don't need to build those algorithms. You can just use algorithms which allow you to have a real-time spatial position estimation, and then you can build on top of it your applications.
Agree
That's
completely. So,
very, I mean, more like, for example, the equivital system that we are using for heart rate monitoring is a very
yes.
interesting system, but it's more invasive. So I mean, for students, like my suggestion would be to start using like system that you can like just put on your body and see what you collect.
One more question, sir.
Yeah.
So, is there any study on the sensors that we are using now? Is there any study of like how harmful it is to the human body if we are keeping it very close to
Ah,
us?
yeah, that's another good question. I mean, there have been like some studies in general for radio propagation, but I mean, I don't think like they are more dangerous than any smartphone. Well,
Oh, okay. I got
when
it.
you have your smartphone, you have like Wi-Fi interface, Bluetooth, cellular. So those systems, it's true that like you put them on your body maybe for a long time, so there may be
Yes.
effects, but it's also true that typically those devices, at least for example the one we are working on, Move to I, it has a very low transmit power because it also needs to save energy. So I'm not aware of any like known like problem created by those devices.
Okay, you see it as less harmful.
Yeah, I mean, right
Okay.
now I don't think it is very harmful.
Okay, great. Thank you so much, sir. Thank you so much for
Okay.
connecting and sharing your knowledge with us. Thank you so much.
Thank you for the invitation.
Thank you so
Okay.
much.
Start.
Bye bye.
Bye bye. Thank you.
Bye bye, sir.
Bye.
I request all participants to please fill in the feedback form. Thank you for joining us. Thank you on behalf of Galgotias University for being part of this session. I'm sure you must have learned a lot from the talk. And in future also, we are going to organize more such events. Thank you for being connected.